These are the notes on solubility and net ionic equations. It'll be helpful to have a periodic table handy and the solubility rules. The solubility rules here are provided for us. There are patterns in these rules, but you do not need to memorize what the rules are. You'll have access to this sheet. And these solubility rules are used to determine the solubility of ionic compounds. So solubility is whether or not it will dissolve, and when we are looking at these, we are looking at in water. So if something is said to be insoluble, that means that it will not dissolve in water, and so its state of matter will be a solid, which we would label as an S. So if we look at finding something that is insoluble, so this one says all bromides are soluble except, and then it lists those here. So lead bromide is insoluble, so we would say that PbBr2 is going to be a solid. If we wanted to show that in a picture, we would put a kind of beaker with water in it, but that lead bromide, PbBr2, would stay together in a compound. It's not going to break up into ions. When we are looking at if something is soluble, that means that it is going to be aqueous in water and it will dissolve in water. And so looking at those bromides again, all bromides are soluble except, so let's look at calcium bromide. Let's say CaBr2. Well, calcium bromide is soluble, meaning that it would be aqueous when in water. And so we could draw our beaker showing what is going to happen. Well, if something is soluble, it is going to break up into ions because that water will dissolve apart those ions. And so we would model something that is soluble by breaking up that ionic compound into the ion parts. So let's determine solubility. For each of these, we're going to determine whether each is aqueous or a solid, so determining that state of matter using your solubility rules and that are on the page above, or if you have the sheet that is provided in class. Looking at this first one, AgNO3, well, our nitrates are discussed in rule number 3. So in rule 3, it says that chlorates, nitrates, and acetates are soluble. And so because this is soluble, it is going to form an aqueous solution, or is going to be aqueous and form a solution. NaCl, and with these, those solubility rules are labeled based on our negative ions, with the exception of the first one, which is talking about ammonia. But we've got chlorides, bromides, iodides. Notice we are looking at those negative ions, and so that's what you're going to look for as you're trying to define the rule. So the second one we had was sodium chloride. All chlorides are soluble except sodium chloride isn't in that list, so that means that it is soluble. And that was by rule 2A, meaning it would be aqueous as a state of matter. Feel free, if you're ready, to try these on your own. Otherwise, I'm going to keep going. BaSO4, so looking at for those sulfates, rule number 4 discusses the sulfates. Sulfates are soluble except, and barium sulfate is on that exceptions list, so it is insoluble, meaning this would be a solid state of matter. PbI2, lead iodide. Iodides are discussed in rule 2C. All iodides are soluble except, and lead iodide is on that exceptions list and is insoluble, meaning it would be a solid state of matter. Ammonium iodide, rule number 1 talks about ammonium. Salts of ammonium and group 1A are always soluble, so we've got this being soluble, so this would be an aqueous state of matter. Calcium carbonate. Carbonate is in rule number 5, all carbonates are soluble. Our carbonates are insoluble except NH4 in group 1 and group 1A compounds. Well, group 1A is the first column on our periodic table. And so we need to check, well, is calcium in that first column on the periodic table? It is not. And so this would be insoluble and would be a solid state of matter. Looking at magnesium phosphate, again, our phosphate rule is rule 5, and it says that phosphates are insoluble except NH4 plus 1 and group 1A compounds. Magnesium is in group 2, it's in the second column, and so it does not fit into the exception, and so this one would also be insoluble and would be a solid state of matter. Lithium phosphate, again a phosphate, that's our rule 5, but lithium is in that first column. It is a group 1 metal, meaning it fits the exception, and so it is soluble, and we would see that lithium phosphate having an aqueous state of matter. A element, because it's in that first column, meaning it does fit that exception, and so that is going to be soluble, and it would have an aqueous state of matter. So again, if we now want to look at what does this mean, soluble means it stays as a solid, aqueous means it is going to dissolve. So let's, for these two in blue, sketch a picture of how the compound behaves on a molecular level. And so let's look at just maybe drawing a beaker with some water in it. Will it dissolve or not? Our lead iodide is insoluble, and so it is going to stay a solid. So we can model that by leaving that lead iodide solid compound together, and then solids generally sink to the bottom. So I always put mine at the bottom of my picture. When we're looking at our aqueous for this lithium phosphate, well, I have 3 lithium ions, so I'm going to put Li plus 1, Li plus 1, Li plus 1, and then I'm going to have my phosphate ion, PO4 minus 3. So I'm going to show all of the ions that this would break up into in that aqueous solution, because that's what's actually happening when something dissolves. It's breaking up into those ions. Remember, water is polar, so it is able to attract those positives and negatives and break those up. So how can we use this information? We're going to spend the rest of these notes writing net ionic equations, which are equations that show only the ions that are participating in a chemical reaction. That means other ions might be there, but aren't actually participating to form something new. This is going to apply to double displacement reactions, where we have a precipitate being formed, and single displacement reactions. In order to get to a net ionic equation, we need 3 parts, and we're going to be showing our work for all of these. We're going to start with our normal equation, which is what we are used to writing. That's going to show everything in the compound. Then we're going to write our complete ionic equation. And remember, ions, if something is soluble, it's going to break into ions. And so we're going to write an equation showing those ions if something is soluble. So our aqueous solutions are going to break apart into ions. Liquid, solids, and gases are going to remain intact. And then after that, we are able to get our net ionic equation, which is what leaves only the things that have changed in our reaction. So we're going to cancel out spectator ions, spectator meaning they're just kind of there watching, spectating the reaction, but not actually participating. And so canceling out those things that don't change from our reactants to our product side. Here's an example of that balanced or regular equation, a complete ionic equation, and then a net ionic equation if you would like. So let's look at this first example of writing a net ionic equation. We've got our normal equation. We're going to write our complete ionic equation and our net ionic equation. We need to go through and write that equation using our charges, making sure we have all of those neutral compounds. I'm going to go through my silver 1 nitrate. Silver has a +1 charge, nitrate has a -1 charge, so I'm going to have AgNO3. I'm going to leave a little space because I'm going to have to predict that state of matter. Sodium chloride, sodium's a +1, chlorine's a -1. So we've got NaCl. Again, I'm going to leave a little space so that I can predict the state of matter. I've got sodium nitrate now. Sodium's a +1, nitrate's a -1. So we've got NaNO3 and our silver chloride +1, -1. We've got AgCl. And I do want to go ahead and balance this if needed. This one is already balanced for us. And now let's predict our states of matter. And we're going to use our solubility rules in order to do that. So looking at my solubility rules, I've got my silver nitrate. My nitrate rule says, number 3, nitrates are soluble, meaning if this is soluble, this will be aqueous. And then I'm going to also do this one over here because I'm already, nope, not that one, sorry. My nitrate rule, because it said all nitrates are soluble, so I'm going to look at my 2 nitrates at the same time. Then I'm going to go to rule 2A, which says all chlorides are soluble except, and sodium chloride is not on my exceptions list, so that means that it is soluble, but my silver chloride is on my exceptions list. And so that one is going to stay a solid. It is insoluble. So now this is balanced. I have predicted my states of matter. Now I'm going to go through and write my complete ionic equation. And so with that complete ionic equation, we are going to take anything that is aqueous and break it into the ions that form. And so we have AgNO3, that's aqueous. So this is going to break up into a silver +1. And then I'm going to put a plus sign to separate those, NO3 -1. And that is that first compound. That's how it would break up into those complete ions. I'm going to do the next with my sodium chloride. So now I have Na +1 plus Cl -1, showing those ions. My NaNO3 is aqueous as well. So I'm going to have Na +1 plus NO3 -1. But when we get to our silver chloride, that would not break into ions. It is going to stay a solid because it is insoluble. And so we are going to keep that together. And that's this rule here. Our aqueous solutions are going to break apart. Liquid, solids, and gases are going to remain intact. And so now to get our net ionic equation, we are going to cancel out spectator ions, which are the things that don't change. And so I'm going to look on both sides of my reaction and see which of those things changed, which did not. So if I look, I have silver +1 on the left, but I do not have a silver +1 on the right, so I can't do any canceling there. Next, I've got my NO3 -1, and I have one NO3 -1 here and one here, so I'm going to cancel those out. Going on to the next one, I've got my sodium. I have a sodium +1 on the left and a sodium +1 on the right, so those are going to cancel. And then my chlorine -1, I don't have a chlorine ion over here, so that can't cancel. So in a double displacement reaction, you are going to always have 2 spectator ions that cancel. Everything else that is left is what is actually participating in the reaction. And so we're going to then copy that down and say, okay, I have a silver ion with a +1 charge. I have a chlorine ion with a -1 charge. And it's those 2 ions then that are reacting to form my silver chloride solid. And so my net ionic equation only includes the things that change throughout my reaction. And then we're done. You are welcome to cross out your spectator ions as long as I have your work of your complete ionic reaction. we can show that as we are, or show our work, and then use that to cancel out what things cancel, leaving us with our net ionic equation. Our last step on this problem is that we are going to sketch what this would look like. We're going to have each of our reactants in their own beaker, showing those with water to see how are they going to behave. Our products are going to go together in the same beaker. And now, just like we did when we were determining solubility, we are going to show how that silver nitrate is going to behave. And since that is aqueous, it's going to break into ions. And so we are going to show those ions, Ag plus 1, NO3 minus 1, in that first beaker representing our first reactant. Our second reactant, sodium chloride, and we can reference our ionic reaction to see what this should look like. That is also aqueous, so we are going to see sodium plus 1, chlorine minus 1. Our products, that reaction has occurred, so our products are going to be together. And again, we can look at the right side of our complete ionic equation. We are going to have sodium ion and NO3 ion, but that AgCl is going to stay together in a solid state, so we're going to leave that as a neutral compound. And I always just put my solid at the bottom when I'm modeling those. Going on to the next example, I already went through and predicted our products and wrote a balanced reaction. Feel free to go ahead and take time to do that on your own. Now, as I look at this, using my solubility rules, I need to predict the states of matter for each of my chemicals. So I've got lead nitrate. My nitrate rule is number 3. All nitrates are soluble, so this is going to be aqueous. That means this is going to be aqueous as well, because remember our nitrate rule, we can look at both of our nitrates at once. Now I'm looking at my chlorides, which is rule 2A on my solubility rule sheet. All chlorides are soluble except, and potassium chloride is not on that list, so it is aqueous, but lead chloride is an exception and it is insoluble, so that will have an S there. So we have our balanced reaction, we have our states of matter, and so now we are able to move on and write our complete ionic equation. This one is a little different because now we have coefficients. I have multiple of things in my compounds, and so we are going to have to deal with a couple of things. First, we've got our lead nitrate. This is aqueous, so it's going to break up into ions. So I've got my Pb plus 2 plus I've got my NO3 minus 1, but I have 2 of those. And so with any of these, your subscript is going to become a coefficient now, because we're listing those separately, so that subscript of 2 is now going to become a coefficient. So we're going to have 2 NO3 ones. Looking on to our next one now, we have a coefficient as well in our next term. So now that coefficient is going to stay a coefficient, and we're going to have to make sure that we distribute it to everything, every ion in that compound. So I'm going to have 2 potassium plus 1s from that coefficient, but I'm also going to have 2 chlorine minus 1s for those ions. Looking at our next side, our lead chloride, PbCl2, is going to be a solid. And then we last have our 2KNO3, which is aqueous. Our coefficient for 2 is going to distribute, so we are going to need 2K plus 1s and 2 NO3 minus 1s for that complete ionic equation. Now as we look at this and getting rid of our spectator ions, those things that don't change, if we have 2K plus 1s on the left, we need to also have those 2K plus 1s on the right. This is by making our subscripts coefficients. It's maintaining the balance we need, and same thing with distributing our coefficients. So looking for what things are the same, a good indicator is if you look at, okay, my lead chloride is what is staying a solid, these other two spectator ions should cancel from my reaction. And I do. I have two K plus 1s on both sides, so those are going to cancel out. I have two NO3 minus 1s on both sides, so those are going to cancel out. My net ionic equation is going to come from everything that is remaining and that didn't get canceled out, because these are the things that are participating in our reaction. So we're going to have a lead plus 2 Cl minus 1 producing our PbCl2 solid. And notice the 2 that we have here is going to match the 2 we have here, because this does need to be balanced. Going through and sketching this just like we did on the last one, each of our reactants is going to get its own beaker. My PbNO32, I'm going to have one lead plus 2 ion, and I'm going to have two NO3 minus 1 ions. In my next one, that KCl, I'm going to have K plus 1, Cl minus 1. I don't need you to put 2 of those in there, but there would technically be 2 of that in there. And then all of our products are going to go into the same beaker at the end. My PbCl2 is going to stay a solid, and then my K plus 1 and my NO3 minus 1 will be there as well. And again, I don't need you to put 2 Ks and 2 NO3s. That's probably better, because then we can see everything being balanced throughout. But we're really just thinking of how are these changing. I don't need your picture to necessarily represent the ratio. Feel free to try the next one on your own or go through it with me. This one was, again, another double displacement, and so it had 2 spectator ions. When we have, and again, the spectator ions, those are the things that canceled. In a single displacement reaction like this one, we should only have 1 spectator ion in a single displacement reaction. I again wrote out my normal equation, making sure that it was balanced. Now, so we have a balanced reaction. Now, using my solubility rules, I need to predict the states of matter. My nitrates, chromium nitrate is soluble, so that will be aqueous. Barium metal is not on your list, but any metal is going to be a solid in its elemental state. So anytime you see a metal solid in elemental state. And then because chromium and barium are switching out, chromium is also a metal, so that is going to be a solid. And then that barium nitrate is aqueous according to our nitrate rules. So we have 2 solids in here, which does make things a little bit different, but our process is the same. Remembering that from our rules up here, subscripts are going to become coefficients, and coefficients stay coefficients. So we've got subscripts and coefficients, so we need to make sure we're paying attention to those here. So we've got coefficients here in actually every term. And so as we're looking at this, we're going to have 2 chromiums, so 2 Cr plus 3s. Chromium's got a plus 3 charge. Plus, well, I have 2, but I also have that 3, so I'm going to actually have 6 NO3 minus 1s. I am going to combine that subscript, makes this a 3 NO3, but then I also have 2 of those, so that's going to become a 6 nitrates. Plus, our solids are going to stay, so we're going to have 3 barium solids, and we include the state of matter when we're writing those, so we know why we didn't break them up. Then we've got our 2 chromium solids plus 3 barium plus 1s plus 3 times 2, 6 NO3 minus 1s. Excuse me, barium is a plus 2. I don't know why I have a plus 1 there. All right, now as we go through, this is our complete ionic equation. Looking for those spectators, we should have 1 spectator ion, and we only even have 1 so our 6 NO3 minus 1s on both sides. And again, you need to have that same number in front. So if those numbers are different, go back and check. Did you take care of your subscripts correctly? And did you include your coefficients throughout? And our spectator ion is those nitrates. And what we're left with then is everything that does not cancel from our complete ionic equation. So we're going to have 2 chromium plus 3s plus 3 neutral bariums, which are solid. And then we have our 2 chromium solids on the other side plus our 3 barium plus 2s. I don't have us modeling this one, but we would model it the exact same way we had previously. If you want to do the last one and then check your answer, here is the answer for you. Feel free to pause the video. Reach out to your teacher with any questions.